This is SpaceTime, Series 29, Episode 14, for broadcast on the 2nd of February 2026. Coming up on SpaceTime, new clues about where Earth's water came from, fresh data about what really lies beneath the surface of the volcanic world of Io, and how shifting tectonic plates may have driven planet Earth's climatic swings. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
A new study claims an analysis of the lunar surface is setting a hard limit on the amount of water which could have arrived on Earth as a result of asteroid or comet impacts. One hypothesis suggests that it condensed out of the same protoplanetary disk as the rest of the material that formed the early proto-Earth 4.6 billion years ago. However, another idea is that the early proto-Earth would have been far too hot to retain any water. And so the water we wound up with today must have arrived later, probably carried in as a result of comet or asteroid impacts. Now, a new study reported in the journal PNAS, the Proceedings of the National Academy of Sciences, suggests that even given generous assumptions, comets and asteroids could only have ever supplied a small fraction of Earth's total water budget. The findings are based on a new analysis of oxygen isotopes in lunar regolith brought back to Earth by the Apollo moon missions. The study's lead author, Tony Gagano from the University of New Mexico, says Earth has erased almost all of its early bombardment record through tectonics, erosion, and constant crustal recycling. The Moon, by contrast, preserves a continuous accessible archive, the lunar regolith, the loose layers of debris and dust produced and reworked by millions of impacts over billions of years. Ever since the Apollo missions, scientists have been trying to read that archive using elements that concentrate on impactors, especially metal-loving siderophile elements, which are abundant in meteorites but scarce in the moon's silicate crust. The problem is, regolith is an especially challenging mixture. Impacts can melt, vaporize, and rework material repeatedly. And then there are the post-impact geological processes which can separate metal from silicate, complicating attempts to reconstruct the type and amount of impactor material. Gagano says, put simply, the regolith on the lunar surface acts like a long-term mixing layer. It captures impact debris, stirs it up, and then preserves it together with new additions for immense spans of time. And this is why it's such a powerful archive. It lets scientists study what really is a time average record of what's been hitting the Earth-Moon system. But instead of relying on metal-loving traces, the new study looked at oxygen, the dominant element by mass in rocks, and specifically oxygen's triple isotope fingerprint to separate two competing signals that normally get tangled together in lunar regolith. That is, the addition of meteorite material and the isotopic effects from impact-driven vaporization. By measuring offsets in the oxygen isotope composition of the regolith, the authors found that at least around 1% by mass of the regolith consists of impactor-derived material that's best explained from carbon-rich meteorites that were partially vaporized upon impact. Gagano says triple oxygen isotopes help distinguish impactor fingerprints from regolith that has a complicated history. So the authors were able to translate these impactor fractions into water delivery amounts. They then translated and multiplied these figures to fit the Earth. They found that even if planet Earth had experienced 20 times the impactor flux of the Moon, the total amount of water delivered to Earth by asteroid and comet impacts would only have amounted to just a few % of an Earth ocean at most. Gagano says the main takeaway from this study is that Earth's water budget is hard, if not impossible, to explain if one only considers water-rich impactors from the outer solar system. Now, to be clear, the results don't say meteorites, asteroids and comets didn't deliver any water to the Earth, just that it could not have been very much, certainly not enough to have been the dominant source of planet Earth's oceans. This is SpaceTime. Still to come, fresh data about what lies beneath the surface of the volcanic world of Io and how shifting tectonic plates may be responsible for driving Earth's climatic swings. All that and more still to come on SpaceTime. NASA's Juno spacecraft has observed an unprecedented volcanic event on the Jovian moon Io, which has provided new insights into what goes on beneath the Ionian surface. Io is the most volcanically active world in our solar system. Whereas other places have weather reports, Io has volcanism reports, with fresh eruptions taking place in, say, the northwest, lava flows increasing in the south, and fresh magma lakes forming in the east. Now, new observations taken by the Juno spacecraft during a close flyby of Io in December witnessed the most energetic eruption ever detected on this 3,660-kilometre wide moon. The findings, reported in the Journal of Geophysical Research Planets, describes an eruption which affected an extremely vast area, some 65,000 square kilometres, in part of the moon's southern hemisphere. The observations by the Juno spacecraft's Jovian infrared auroral mapper indicate an energy release of between 140 and 260 terawatts, a value that far exceeds those of the most significant eruptions previously observed on Io. The study's lead author, Alessandro Mura from the Italian National Institute for Astrophysics, says what made this event even more extraordinary was that it didn't involve a single volcano, but multiple active sources that all lit up simultaneously, increasing their brightness by more than 1,000 times compared to typical levels. This perfect synchrony suggests that it must have been a single enormous eruptive event propagating through the subsurface for hundreds of kilometres. The results suggest the existence of what must be enormous interconnected magma reservoirs deep beneath Io's surface. Reservoirs capable of being activated simultaneously and producing planetary-scale energy release. Mura says the observations provide direct evidence that Io's volcanism is being powered by deep interconnected magmatic systems. At the same time, other nearby volcanoes weren't involved in the eruption, adding unexpected elements of complexity to the functioning of Io's interior. Future observations may reveal whether the eruption left new lava flows or ash deposits on the Ionian surface, and that would provide further clues about the moon's geological evolution and the very nature of its extreme volcanism. This is SpaceTime. Still to come, how shifting tectonic plates may have driven planet Earth's climatic swings. And later in the science report, scientists detect traces of Chinese radioactive nuclear waste which has travelled all the way down into the West Philippine Sea. All that and more still to come on SpaceTime. A new study claims that carbon released by the Earth's spreading tectonic plates may have triggered major transitions between the planet's ancient ice ages and warmer climates, rather than volcanic activity as previously hypothesized. The findings, reported in the journal Communications, Earth and Environment, reconstructed how carbon moved between volcanoes, oceans and deep within the Earth's mantle over the last 540 million years. The study's lead author, Ben Mather from the University of Melbourne, says the findings challenge a long-held view that chains of volcanoes formed by colliding tectonic plates were Earth's main natural source of atmospheric carbon. In fact, the study shows that carbon gas released from gaps and ridges deep under the ocean from moving tectonic plates was instead likely driving major shifts between icehouse and greenhouse climates for most of planet Earth's history. Mather says his team found that carbon emitted from volcanoes around the Pacific Ring of Fire, for example, only became a major carbon source in the last 100 million years, which challenges current scientific understanding. The work provides the first clear long-term evidence that the global climate was shaped mainly by carbon released where tectonic plates pull apart rather than where they collide. The new insight not only reshapes science's understanding of past climates, but also helps refine future climate models. By pairing global plate tectonic reconstructions with carbon cycle modelling, the authors were able to trace how carbon was stored, released and then recycled as continents shifted. The new findings help explain key historical climate shifts, including the late Paleozoic Ice Age, the warm Mesozoic greenhouse world, and the emergence of the modern Cenozoic icehouse. This shows how changes in carbon released from spreading plates shape these long-term transitions to the planet's climate. Mathis says understanding how Earth controlled its climate in the past highlights how unusual the present rate of climate change really is.
Yeah, so one of the questions we had going into this research was to work out what are the main emitters of carbon or CO2 throughout Earth's history. And one of the big findings was essentially that arc volcanoes, this is where oceanic plates get subducted under the continental lithosphere, such as around the Ring of Fire in the Pacific Ocean. These arc volcanoes emit a whole bunch of carbon today, but if you go looking back through time, based on our modelling, we actually find that they decrease in emissions quite rapidly until we get to about 100 million years ago during the late Cretaceous. So actually in mid-ocean ridges, these are the cracks along the sea floor where tectonic plates split apart, are actually the main emitters of CO2 preceding the last 100 million years.
That's interesting because one would have thought a similar sort of process with volcanic activity and magma moving up from the mantle into the mid-ocean ridges, then seafloor spreading, that would have been going on long before that and roughly the same sort of rates.
They roughly have, actually. The amount of CO2 that they emit is generally proportional to the rate of spreading, so the rate that the continents are being split apart, and essentially how long that boundary is, so how many mid-ocean ridge segments there are on the Earth at any one time period. What the difference is that the arc volcanoes at subduction zones, like the Ring of Fire, these arc volcanoes have really ramped up their emissions of CO2. And the reason for that is because we have a huge increase in the amount of deep sea sedimentary carbon that gets recycled into the Earth and eventually spewed out of these volcanic arcs.
Okay, do we know why?
Because of these little critters called phytoplankton, which evolved some 150 billion years ago. And these have calcium carbonate scales and proliferated the Earth's oceans around 150 million years ago. And when these plankton die, they leave immense deposits of calcium carbonate on the seafloor. And as the tectonic plates move and are eventually recycled into the Earth's molten interior by slipping under each other through subduction, these huge reservoirs of stored carbon end up being pushed into the mantle. And then a portion of that carbon leaves the subducting ocean plate and will get mixed into the molten interior. But a portion of that will also get emitted via volcanic arc volcanoes. So yeah, it's really these critters that have evolved in the last 150 million years ago, which have resulted in volcanic arcs being the primary emitter of CO2 today.
It's amazing that tiny microscopic animals and plants that one barely sees other than the general greenness of the ocean can make such consequential changes to the entire planet.
It is, isn't it? Yes, yeah, and this is a key evidence of biological changes that go on within the Earth having a huge effect on the global deep carbon cycle. And previously to this research, it wasn't really well understood exactly how much carbon these little critters can produce on the seafloor. But yeah, through this research, we were able to essentially track the movement of carbon between the seafloor and the Earth's molten interior and the atmosphere, which form this, I guess, deep time carbon cycle.
Tell me how you did the research.
So a lot of the research that I do is to try and reconstruct Earth's history using plate reconstruction. So that's how the tectonic plates all fitted together at any time before the present day, essentially. So in this research, we're looking at the last 540 million years, but we have plate reconstructions now which go to 1.8 billion years ago. And now things get a little bit sketchy the further back you go. And the reason for that is because we have fewer and fewer observations and evidence to go into these plate reconstructions. But nonetheless, we have some plate reconstructions, some ideas and hypotheses of how the Earth looked 1.8 billion years ago. In this research, what we were able to do for the last 540 million years ago was couple these tectonic plates with a model of how carbon moves with the Earth. So we were able to track how fast tectonic plates spread apart, how fast they come together, and the length of those mid-ocean ridges and subduction zones to try and work out how much carbon is being emitted and recycled back into the Earth.
They say pilots want to fly into space. Do people studying mid-ocean ridges want to go down and look at black smokers?
Yes, well, you can actually have an opportunity to look at an active mid-ocean ridge in Iceland. So Iceland is a rare example where you can actually put on your scuba tank and journey into a mid-ocean ridge.
There are parts of Iceland where you can actually be standing on two different plates at the same time without having to get your feet wet.
Yeah. Yes, that's the much warmer option, I'd say.
That's Dr. Ben Mather from the University of Melbourne. And this is SpaceTime. And time now to take a brief look at some of the other stories making news in science this week with a science report. A new study claims climate change made the intense January heat waves in Australia 5 times more likely. The findings by Imperial College London also show that the heat waves happened against a backdrop of a weak La Nina, which usually brings far milder temperatures to much of eastern Australia. Across southeastern Australia, maximum temperatures during January were consistently above 40 degrees Celsius, the area sweltering through its hottest temperatures since the infamous Black Summer of 2019-2020. In Melbourne, temperatures often topped 44 degrees, with hospitals reporting emergency admissions were up by as much as 25%. While Port Augusta in South Australia was just one of many outback communities where temperatures reached more than 50 degrees Celsius, making them among the hottest places in the world. All that heat triggered devastating wildfires across Victoria, leading to a state of disaster being declared. The new analysis shows that in today's climate, Australia can now expect to experience similar heatwave conditions roughly once every 5 years. Doctors have breathed a sigh of relief after successfully keeping a patient alive for 48 hours without lungs. The medical marvel, reported in the journal Med, used an artificial lung system to help a 33-year-old patient breathe for 2 days after he required both his lungs to be removed as a complication of a severe flu infection. The man's lungs had deteriorated rapidly due to bacterial pneumonia. So the surgeons decided to on-the-spot engineer an artificial lung system that pumped out the blood, removed carbon dioxide from it, and then filled it with fresh oxygen before returning it to the patient, bypassing the need for physical lungs. The man was then able to spend 2 days recovering from the infection, which the medical team says was enough time for him to become stable enough for a double lung transplant, and now, more than 2 years later, the patient has returned to daily life with good lung function. Scientists have detected Chinese radioactive nuclear waste, which has travelled all the way down to the West Philippine Sea. The findings by the Philippine Nuclear Research Institute, the University of the Philippines, and the University of Tokyo found higher levels of radioactive iodine-129 in local seawater samples off the Philippine coast. Scientists tested 119 samples from different parts of Philippine waters, finding that iodine-129 levels in the West Philippine Sea were between 1.5 and 1.7 times higher than in nearby regions. Now, this isotope is commonly produced by nuclear reactors and by thermonuclear weapons testing. The authors say the contamination was carried by ocean currents from the Yellow Sea area on the Chinese coast. There, Chinese nuclear fuel reprocessing plants and leftover contamination from Cold War nuclear tests probably released the radioactivity into the rivers, which then poured it into the Yellow Sea, and from there, into the world's oceans. A new hypothesis claims pareidolia may be linked to a rare neurological condition, which can cause a constant type of visual static in some people. The skeptic's Tim Mendham says if proven correct, the idea might offer a unique window into how an overactive brain may amplify erroneous illusionary patterns it sees.
Pareidolia is the phenomenon of seeing shapes, familiar shapes, in surfaces, in clouds, in trees, whatever, seeing certain shapes, figures in those things. And the most common one is faces, because we're so used to seeing faces that becomes just part and parcel. Faces in toast, faces on the front of cars, taps. We are ready to see 2 eyes and a mouth, and perhaps a nose as well, everywhere. That's face pareidolia. But pareidolia is generally seeing...
But we're actually wired to do that, aren't we? That was a survival technique of our ancestors.
That's right. I mean, the face is the thing because you see it so much as a baby. For example, people staring at you, faces. So you get used to faces, happy faces, sad faces, whatever. But yes, we are wired to find shapes, to try and find patterns where the patterns don't necessarily exist. So it gives us some sort of stability, if you like. A theory that's been put forward lately is that people who are suffering from visual snow syndrome are more likely to have pareidolia experiences than those who don't. Now, visual snow syndrome is basically static in how you see things. There's a lot of dots in front of your eyes that confuse the image somewhat. Now, there's an obvious problem here is that if people suffering from visual snow syndrome should have a less clear vision, right? I mean, if you're seeing things through static or through an interference pattern of what you're looking at, it's hard to concentrate and hard to focus. So it's not surprising that when you squint, you can see funny shapes and things which don't exist when you look at something more clearly. So to suggest that it might be the case that people who suffer from this are more likely to have pareidolia experiences, especially seeing faces and things, than those without. That's fine. It doesn't tell you a lot apart from the fact that they can't see things very well. They put it down to this whole syndrome of visual snow as hyperexcitability in the visual cortex, which means you tend to try and find a logical explanation for what you're seeing, perhaps because they have this problem of focusing of a distraction to how the visual images they have. And therefore, they try desperately to find something in there, and they might be more inclined to see faces. And one of the big problems with the study, the red flag pops up straight away, was they asked the people they surveyed to rate on a scale from 1 to 100 how easily they could see a face in a range of images that were being shown. So in other words, they're wanting people to start with to say, yeah, this is what we want you to say you are seeing, or want you to talk about you are seeing, rather than just say, do you see anything interesting in this photo or this image? They say, do you see faces in this image? And therefore people will look for faces. It's like saying to someone, don't think of a rhinoceros, and naturally you think of a rhinoceros. You can't get it out of your head after that. Instantly there's a problem with that survey, that particular survey. And it might be a thing that because people have worse vision, they tend to see shapes that aren't there more than other people do. We all do it. It's nothing particularly sort of worrisome or anything like that. But to suggest that it just might be a condition that people with bad eyesight see pareidolia and see faces more often than those who don't, because their focus is less clear. Maybe as you get older, you'll see more faces as your eyesight deteriorates.
That's the Skeptic's Tim Mendham, and this is Space Time. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from SpaceTimeWithStuartGarry.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to SpaceTimeWithStuartGarry.com for full details.
You've been listening to Space Time with Stuart Gary. This has been another quality podcast production from Bytes.com.